Every year in the United States, flash floods kill more people than tornadoes, more than hurricanes, more than lightning, more than any other severe weather phenomenon that gets its own dedicated warning system, its own season, its own cultural awareness campaigns. The average annual death toll from flash floods in the United States is approximately 127 people per year. Tornadoes 70, hurricanes 47, lightning 49. Most people, asked to rank the deadliest weather hazards in America, would not put flash floods first. Most people would not put flash floods second. The hazard that kills more Americans than tornadoes and hurricanes combined sits at the bottom of the public awareness hierarchy, below the hazards that receive wall-to-wall media coverage when they occur, below the hazards that have dedicated federal preparedness infrastructure, below the hazards that people in at-risk regions actively plan for. Flash floods kill more. They are prepared for less. And the mechanism by which they kill, the physics of moving water in confined terrain, is so counterintuitive that the single most common decision people make when they encounter one is the exact decision the physics says will get them killed. Flash floods are defined by their speed of onset. They develop within 6 hours of a triggering rainfall event, and often much faster. They differ from river floods in a fundamental way. A river flood develops over days as a drainage basin accumulates rainfall and the river rises progressively. A flash flood can develop in minutes, in a location that shows no sign of imminent inundation, triggered by rainfall that is happening kilometers away. This geographic disconnect between cause and effect is the central feature of flash flood lethality. You can be standing in full sunshine in a canyon with no cloud above you, while a thunderstorm 30 kilometers upstream is releasing water that will reach your location concentrated, accelerated, carrying sediment and debris in under 20 minutes. The National Weather Service issues approximately 5,000 flash flood warnings per year in the United States. Of those, roughly 40% result in no significant flooding. They are precautionary, based on upstream rainfall that dissipated before producing dangerous runoff. The false alarm rate conditions people to discount the warnings. And in the 60% of cases where the warning is accurate, the window between warning issuance and flood arrival is often shorter than the time required to evacuate a low-lying area. In this video, we'll cover 3 things: the physics of why water moving at flash flood velocities exerts forces that are counterintuitive to anyone who hasn't experienced them, and why 15 centimeters of water in a channel can knock down an adult. The specific mechanism that makes clear sky floods in canyon environments the deadliest expression of flash flood risk, and the one behavior pattern that appears in the case files of flash flood fatalities with a frequency that makes it the single most actionable point of intervention in the entire hazard category. We start with the physics of moving water. Water is approximately 800 times denser than air. This single fact explains why moving water at speeds that feel unremarkable a walking pace. A slow jog produces forces that bear no relationship to what those speeds suggest in any other medium. Force in a moving fluid depends on density, velocity, and the surface area being acted upon. At the same speed, water exerts approximately 800 times the force of wind on a given surface. A wind of 15 kilometers per hour, barely enough to rustle leaves, is negligible. Water moving at 15 kilometers per hour exerts a force equivalent to a sustained wind of roughly 420 kilometers per hour on the same surface. This is why the numbers in the title of this video are real, not exaggerated. 15 centimeters of water ankle depth moving at 2 meters per second exerts a lateral force on an adult human leg of approximately 135 kilograms. The average person cannot maintain their footing against 135 kilograms of lateral force. They fall, once horizontal in moving water of any meaningful depth. The body presents a much larger cross-sectional area to the current. The force increases dramatically, and regaining a standing position becomes impossible without a fixed anchor. 60 centimeters of moving water, roughly knee depth, on a short adult exerts sufficient force on a typical passenger vehicle to lift the wheels from the pavement and begin moving the car laterally. A car weighing 1,400 kilograms becomes buoyant in less than 60 centimeters of standing water and subject to lateral displacement in even shallower moving water. The point at which a vehicle is no longer under the control of its driver in flash floodwater is well below the point at which it looks alarming from the outside. This is the mechanism behind the most common flash flood fatality scenario in the United States. A driver encounters water across a road. The depth appears manageable. They enter the water. The vehicle is displaced or stalled. The driver cannot exit against the current. The water rises. The National Weather Service has a campaign for this turnaround don't drown specifically because vehicle-related incidents account for approximately half of all flash flood fatalities annually. The force calculation changes dramatically with terrain. In an open floodplain, water spreads laterally as it rises, distributing energy across a wide area and reducing the depth and velocity at any single point. In a canyon, a gorge, a road culvert, or any confined channel, there is no lateral spreading. The water has nowhere to go except forward. Depth and velocity both increase simultaneously. This is the canyon amplification effect. A volume of water that would be 30 centimeters deep in an open valley may be 3 meters deep in a canyon of equivalent width, and because velocity in a confined channel increases with depth and gradient, that same water may be moving not at 2 meters per second, but at 6 or 8. The force relationship is not linear with velocity, it scales with the square of velocity. Water moving at 8 meters per second exerts 16 times the force of water moving at 2 meters per second. And in canyon terrain, that water arrives with a leading edge. When rainfall in a mountain watershed generates rapid runoff into a confined stream channel, the water doesn't arrive gradually, it arrives as a bore, a steep, turbulent wall of water, often loaded with sediment, rocks, and uprooted vegetation. That moves faster than the water behind it because it is being driven by the hydrostatic pressure of all the water accumulating in the channel above. The bore can be traveling at 20 to 40 kilometers per hour. It may be 2 to 4 meters tall. It sounds like a freight train, a deep rumble and roar that precedes it by seconds, not minutes. People in canyon environments and slot canyons in Utah and Arizona, in mountain stream beds in the Alps and Rockies, in river gorges used for canyoneering and hiking worldwide describe hearing this sound and having between 5 and 30 seconds before the bore arrived. In a slot canyon where the walls are vertical and there is no higher ground to reach, 30 seconds is not enough time. In many documented incidents, it was not enough time to even communicate to others in the group what was happening. The flood gives you a sound. The terrain determines whether that sound gives you enough time to survive. August 12, 1997. Antelope Canyon, Page, Arizona. Antelope Canyon is one of the most photographed natural features in the American Southwest, a slot canyon carved by water into Navajo sandstone, its walls curved and colored by millennia of flash floods. On August 12, 1997, 11 tourists were inside the lower canyon section with a guide. The weather at Page, at the canyon entrance, was clear. 27 kilometers away, a thunderstorm was releasing heavy rainfall into the watershed above. The flood bore that entered Antelope Canyon that afternoon was estimated at 3.7 meters tall. It traveled the length of the lower canyon in minutes. 12 people died, the guide, and 11 of the 12 tourists. One tourist survived by climbing a fixed rope that happened to reach a ledge above the flood level. The National Weather Service had issued a flash flood watch for the region that day. The warning was not posted at the canyon entrance. The guide, who had taken groups through the canyon many times without incident, assessed the conditions at the surface and judged the risk as acceptable. The Antelope Canyon flood is the most documented slot canyon flash flood fatality event in U.S. records precisely because it happened at a well-visited location with a clear pre-event record, making the investigation unusually complete. The post-event analysis identified several factors the watch was issued but not communicated to guides operating in the canyon. There was no rain gauge upstream capable of issuing automated alerts, and the guide's risk assessment, based on visual conditions at the surface, had no mechanism to incorporate upstream watershed conditions. All 12 deaths were caused by the bore arriving faster than any person could exit the canyon on foot, in terrain that offered no lateral escape. July 31st, 1976, Big Thompson Canyon, Colorado. The Big Thompson River runs through a steep canyon in the Front Range of the Rocky Mountains, 80 kilometers northwest of Denver. On the evening of July 31st, a slow-moving thunderstorm stalled above the upper watershed and released approximately 30 centimeters of rain in 4 hours, the equivalent of a year's average precipitation for the area, delivered in a single evening. The resulting flood wave carried an estimated 218,000 cubic meters of water per minute through the canyon at peak flow of volume sufficient to move boulders weighing hundreds of tons. 143 people died. Most were in vehicles on the canyon road, attempting to drive out. Others were in cabins along the river. A small number were camping in the canyon floor. The Colorado State Patrol officer who responded to the Big Thompson flood issued what became standard flash flood guidance. Climb to safety, do not try to drive out. Of the people who followed that instruction and climbed the canyon walls rather than attempting to drive, the survival rate was significantly higher than among those who tried to use the road. The pattern is identical to Antelope Canyon 2 decades later confined terrain, distant rainfall, rapid onset. Here is the detail about flash floods in canyon terrain that changes everything about how you assess the risk of being in one. Standard weather awareness, the kind that most people apply intuitively when they're outdoors, is sky-based. You look up. If the sky above you is clear, you are not in immediate weather danger. This heuristic works for lightning, for hail, for tornadoes, for most forms of precipitation-driven hazard. The sky above you tells you what's happening to you. In a canyon watershed, the sky above you tells you what's happening in the canyon you're standing in. It tells you nothing about what's happening in the watershed above you, the terrain that may extend 30, 50, or 100 kilometers upstream, draining into the channel you're currently in, funneling every drop of rain that falls anywhere in that entire area into the single corridor where you're standing. The Big Thompson watershed covers approximately 1,300 square kilometers. Antelope Canyon's upstream watershed extends more than 25 kilometers into terrain not visible from the canyon entrance. In both cases, on clear sky days at the canyon location, a weather event in the upstream watershed was producing the conditions for a fatal flood in the downstream corridor. This is the counterintuitive geography of flash flood risk. You are not assessing the risk of the weather above you. You are assessing the risk of the weather above your entire upstream watershed, a region you cannot see, whose conditions you cannot assess by looking at the sky, and whose rainfall will arrive at your location concentrated, accelerated, and carrying everything it has collected on the way. The implication for anyone spending time in canyon terrain is specific and not intuitive before entering a slot canyon, a river gorge, a desert wash, or any confined channel with an upstream watershed. The relevant weather check is not the weather at your location. It is the weather in the entire upstream drainage area, which requires a different kind of forecast, from a source that provides watershed scale data rather than point location data. The National Weather Service flash flood guidance provides this information. The challenge is that the mental model required to use it, visualizing a large upstream area, and understanding that rainfall anywhere in that area is relevant to your safety, is not the same mental model people apply when checking whether to bring an umbrella. At Antelope Canyon, the guide checked the sky at the canyon entrance. The sky was clear. The storm was 27 kilometers upstream in an area the guide could not see from the entrance. Both of those facts were simultaneously true. The sky assessment was accurate. The risk assessment was fatally incomplete. The United States numbers 127 deaths per year, represent a country with one of the most developed flash flood warning systems in the world, with extensive USGS stream gauge networks, next-generation radar coverage of virtually the entire country, and a National Weather Service that issues approximately 5,000 flash flood warnings per year. The global picture is categorically different in scale. Flash floods are the leading cause of weather-related death worldwide. The World Meteorological Organization estimates that floods, of which flash floods constitute the most lethal subset, account for approximately 40% of all natural disaster deaths globally. In a typical year, flash floods kill between 5,000 and 8,000 people worldwide. In years with major events, that number is substantially higher. South and Southeast Asia experience the highest flash flood fatality concentrations on Earth. The combination of monsoon rainfall patterns, which can deliver extraordinary volumes of precipitation in short periods, steep terrain in the Himalayas, Hindu Kush, and surrounding ranges, and dense population in the river valleys below creates the conditions for repeated catastrophic flash flood events. In 2020, flash floods and landslides triggered by monsoon rainfall killed over 2,400 people across Nepal, India, Bangladesh, and Pakistan in a single season. Pakistan's 2022 flood season, driven by an exceptionally intense monsoon, amplified by above-average temperatures, killed over 1,700 people and displaced 33 million. A significant proportion of the fatalities were flash flood events in the mountainous north and west, where river channels overwhelmed by rapid snowmelt and intense rainfall produced bore events in populated valleys with minutes of warning. The Mediterranean flash flood pattern is distinct from the monsoon model, but equally lethal. The combination of dry summer conditions that harden soil surfaces and reduce infiltration capacity, followed by intense autumn thunderstorms, produces runoff rates that can overwhelm drainage systems in minutes. In September 2020, flash floods in the Gard region of southern France killed 21 people in a single event, flooding that developed in under 2 hours. In terrain with historical flash flood records going back centuries. And in a country with sophisticated meteorological infrastructure, in October 2021, flash floods in Sicily killed 10 people when a campsite in a river gorge was inundated overnight by a storm that developed faster than the warning system's lead time. The infrastructure dimension of flash flood scale extends well beyond direct fatality counts. Road and bridge infrastructure is disproportionately vulnerable to flash floods because roads and bridges are built in the lowest lying terrain valley floors, canyon bottoms, river crossings, which is exactly where flash flood forces are concentrated. The American Society of Civil Engineers estimates that hydraulic action from flood events is the leading cause of bridge failure in the United States, accounting for approximately 60% of all bridge collapses. When a bridge fails during a flash flood, the consequences extend beyond the immediate fatality risk to people on the structure at the moment of failure. Roads become impassable. Emergency response is delayed. Communities in mountainous or canyon terrain, which often have single road access, can be isolated for hours or days. The 2013 Colorado floods, which included extensive flash flooding across the Front Range, destroyed or damaged over 200 bridges and closed approximately 500 kilometers of road, cutting off dozens of communities for periods ranging from days to weeks. The climate trajectory for flash floods follows the same pattern as ground saturation risk warming, driven intensification of extreme short-duration rainfall events. The physics is straightforward. A warmer atmosphere holds more water vapor, and when precipitation occurs, it tends to be more intense. For flash flooding specifically, the relevant metric is not total annual rainfall, but peak intensity. How much rain falls in 1 hour, in one canyon watershed, above one population. A 2019 analysis in the journal Nature found that extreme short-duration rainfall, the kind most associated with flash flood generation, has intensified significantly across Europe, North America, and parts of Asia over the past 4 decades, with the trend accelerating in the most recent decade. The increase in peak rainfall intensity is not uniform. It is most pronounced in regions that already experience high flash flood frequency, creating a pattern where the most exposed communities are subject to the most accelerating risk. The Turnaround Don't Drown campaign launched by the National Weather Service in 2003 has produced measurable reductions in vehicle-related flash flood fatalities in the United States. Research published by NOAA found that in the years following the campaign's launch, deaths from driving into flooded roadways declined by approximately 25% relative to pre-campaign trends. The campaign works because it addresses a specific, modifiable behavior with a specific, simple instruction. The equivalent campaign for canyon environments stay out of slot canyons and river gorges when flash flood watches exist for any part of the upstream watershed does not yet have the same cultural penetration. The Antelope Canyon disaster produced local policy changes at that site. It did not produce the equivalent of Turnaround Don't Drown for canyon recreation nationally. That gap remains open. Think about a road you drive regularly. Not a dangerous road, a normal road. A commute road, a road you've driven dozens or hundreds of times without incident. Somewhere on that road, there is likely a low point, a dip where water collects after heavy rain, a crossing over a small stream or drainage channel. a section where the road descends into a valley or canyon and then climbs back out. A concrete ford with depth markers that you've never seen with water on it. Most of the time, that low point is exactly what it looks like, a minor topographic feature on an unremarkable road. But that low point has a watershed. Every drainage channel has an upstream catchment area, a region of terrain that funnels its rainfall into that channel. You probably don't know how large that watershed is. You probably don't know what the historical flash flood record on that channel looks like. You almost certainly don't check the upstream watershed weather conditions before driving that road on a day when there's a thunderstorm somewhere in the vicinity. Most people don't. The risk is invisible in good conditions and appears with little warning when conditions change. And the force of 60 centimeters of moving water on your vehicle, the force that lifts a 1,400 kilogram car off the pavement, arrives before the water looks dangerous from a driver's seat. Here's what changes about how you see that road after this video. The sky above the low point tells you nothing about what's in the watershed above it. A clear sky at your location and a thunderstorm 30 kilometers upstream are not mutually exclusive. They were simultaneous at Antelope Canyon on August 12, 1997. They were simultaneous at Big Thompson Canyon on July 31, 1976. They are simultaneous somewhere every flash flood season. The rule is specific if there is a flash flood watch or warning for any part of the region you're in. The water crossing you've driven 100 times in dry conditions is not the same road. The physics of what that crossing can become in under 20 minutes from a storm you can't see is categorically different from the crossing you remember. Turn around, don't drown. 4 words that have saved hundreds of lives. The physics behind them is in everything you've just watched. The sound you almost heard at the end of that shot is what people in canyon environments describe hearing between 5 and 30 seconds before the bore arrives. Tell me in the comments, did you know, before this video, that flash floods kill more Americans every year than tornadoes? Next week on ERTH, the New Madrid seismic zone. Most Americans who think about earthquake risk think about California, about the San Andreas, about the big one. But the fault system that keeps geologists and FEMA most concerned is not in California at all. It's in the middle of the country, under flat terrain, in states with essentially no earthquake-resistant infrastructure, and it last produced 3 magnitude 8 or greater earthquakes in a single winter in 1811 and 1812. The science of what would happen if it ruptured today is not what most people in the affected region have ever been told. See you then.